Welcome everyone to this session. It's now 1 o'clock, so I'll introduce our speakers. Right now we have Ming, Gong, Paul Rose, and Anthony Chang, who will be talking about their solution to A Dog Cannot Catch. Go ahead.
Alrighty. Sorry. So in this presentation, we will define our approach to the problem, explain our assumptions, create and analyze our mathematical model, and finally explore the model limitations and how it can be improved in the future. So to approach this problem, we first made an ODE model of Fritz's jaw movement and tracked Fritz's mouth in a video to corroborate the model and determine which constants to use in the ODEs. Then we modeled errors in head orientation and distance prediction using kinematics and determined how these would affect catching ability. And finally, we estimated the effect of the initial throw, object size, and air resistance. So there are three main factors that can cause Fritz to fail. The first two stem from Fritz losing sight of the food when his mouth is open, requiring him to calculate the parabolic trajectory from that point on in his head. This leads to potential errors in positional prediction, as well as errors in mouth timing. And the third main type of error stems from elongated shapes, where a successful catch requires rotational prediction and the twisting of the head by the right angle, as in the melon example on the right. So in this respect, we took a different approach from other teams because some other teams focused on the movement of Fritz to the intended position, whereas we assumed that Fritz could move to where he intended perfectly and that observational errors were the main causes of failures.
We made the following assumptions. The object is spherical and the mouth of the dog is circular, so the radius is uniform. The object is not deformable. The dog moves to the correct left-right position and longitudinal orientation before the catch. For the mouth to successfully catch the object radius big R must be less than the effective mouth radius, which is composed of the following three parts. The mouth radius denoted by R of t multiplied by the orientation angle error, cosine of theta, and subtract a positional offset delta of x.
And now let's define our coordinate system. Let's let the y position of Fritz's cheek be 0 and the x position of the throwing hand be 0. And therefore, we can let the object's initial thrown position be 0, y 0, and the initial velocity be x prime 0, y prime 0. And finally, we measured the nose is 6.5 centimeters above the cheek. And we let the mouth radius be half the distance from the nose to the chin, here to r. And let time be equal to 0 when the object is thrown. As shown in the diagram, there are three critical times for the catch. When the dog starts opening the mouth, defined as TA. When the object reaches the mouth opening, defined as TB. And when the object reaches the cheek, defined as TC. We want to find the effective mouth radius, R, at time TB when the object passes through the mouth opening.
So to model the motion of the dog's mouth to calculate which timings result in a successful catch, we interpreted the jaw as a moment arm and the jaw muscles as a source of torque and interpreted the system via a damped driven harmonic oscillator. Such a system can be described by an ODE using moment of inertia, I, friction constant C, and spring constant K to relate the various derivatives of angle. This torque-based ODE describing the jaw as a hinge can then be converted to a force-based ODE by dividing by the length of the moment arm. And then to solve this ODE, we used e to the st substitution and a quadratic. And we also assume that the system is opened over damped, as the dog's mouth does not continue to oscillate after it opens and closes the first time. And for constant driving force, the particular solution is given by F over K, and the total solution is the sum of both of these solutions. However, F cannot be a constant driving force as the mouth opens and closes. So we assumed F of t to be a square bump and solved the ODE for opening force F1 and closing force F2, which is negative. If the applied force switches from F1 to F2 at time t, position and velocity of the first solution at time t can be used as the initial conditions for the second solution. This yields a piecewise function, r of t, that's continuous and differentiable. Now we need to find values for the various constants in the model that match how Fritz's mouth actually behaves.
Back a little bit. Here we have two clips. One of them is Fritz trying to catch a taco, and the other one is Fritz trying to catch a burrito. If you watch the compilation video by the Fritz dog, you'll probably find these clips in the video. However, in these clips, we noticed that there are boxes and colorful points following Fritz. We created these annotations by training Ultralytics's yellow V8 on the Stanford dog dataset. The Stanford dog dataset is a compilation of many dogs with point annotations for specific parts of the dogs, like the legs, paws, ears, but more importantly for us, the chin and their nose. We chose to take a clip with a smaller food object so it wouldn't obstruct as many points that we would need. In this clip, the dog is attempting to eat what appears to be a meatball. A few recorded points were inaccurately positioned, although the majority were correctly positioned. To address this issue, we manually identified and fixed these points. After averaging a list of points together and doing the necessary conversions, like removing the distance between the chin and the bottom of the mouth, we were able to obtain this graph. The red data points correspond to the instance when Fritz started opening its mouth and finished. Note the dip and rise after the red data points. This can be attributed to a latch-this effort by Fritz to seize the meatball by slightly closing his mouth and opening it again. With our data points, we adjusted our model's constants to match with our graph. Here's an overlaid plot of the two graphs together.
So Fritz wants the mouth to close when the object reaches its cheek. Otherwise, the object may cause choking or just bounce out of the mouth. The mouth opens at TA and closes at TC. And the time interval T-chomp, based on our model, is approximated to be 0.45 seconds. The difference between TV and TC is the time for the object to go through the mouth, which is approximately the mouth length over the falling speed, assuming the speed at TV and TC are close enough. And from the graph here, we already see a problem. For a fast falling object, the mouth cannot open wide enough at TB, and in fact, it's almost closing. And when Fritz opens his mouth, line of sight of the object is blocked, so he tends to assume the object continues in a straight line. And Fritz determines TA, we assume, based on the tangent line approximation of the current position and velocity, which can be derived from this equation. And before opening the mouth, Fritz can still adjust for positional error by realigning, and we found it usually not too difficult in the videos. And once the mouth opens, however, the line of sight is lost, so observational errors can no longer be adjusted for using visual feedback. This leads to positional and timing errors, which cannot be easily adjusted. And we add a subscript 1 to denote Fritz's perceived time based on the linear approximation, and 2 for the actual time. Here are the calculations for the time and velocity at the time when Fritz thinks the object reaches its cheek and when it actually reaches its cheek. And we ignore the air resistance for now, assuming the x velocity stays constant, and we'll come back to air resistance later. And then the x position error due to parabola misestimation, delta x, will be this formula, which is the product of the x speed, the time difference between reality and approximation, delta t, and the sine of the trajectory's latitudinal angle.
Now we will quantify how the dog's misestimation of latitudinal head orientation affects the catching outcome. The projection of the mouth width r onto the normal of the trajectory gives the width the food has to pass through if it's going to be caught successfully. This width is given by r times cosine of delta theta. Orientation error is affected by the tangent line approximation the dog makes for the parabola. The food's path curved downward in the period when the dog can't see the food. The adjustment for this is not significant until delta theta becomes very large, however. Even if the dog is 20 degrees off, the effective mouth width is still 93% of what it would have been had the dog's head been perfectly aligned. Thus, the dog does not have to orient its head very precisely to catch the food successfully. So we can now bundle the mouth and kinematics models together to calculate the size of the largest object the dog can catch in different conditions. Here, delta x is a function of initial height and velocity components of the throw. Thus, the effect of different throw properties on catching success can be analyzed. For now, the food is assumed to be spherical and air resistance is assumed to be negligible, but these factors will be addressed later.
And now let's analyze the different factors. So we first simulated the effect of different x and y initial velocities on the maximum catching radius. So from this graph, like we set the x-axis to be the initial y speed and observe like the different factors of the initial x speed. So from the graphs, a high x velocity makes the catching harder due to greater positional error from the parabola miscalculation. And similarly, a low y velocity also amplifies the positional error as the object takes longer to fall. So there's more error between the linear and tangent and the quadratic approximations. And a high y velocity also makes catching harder due to mechanical limits on how fast the mouth can open and close. And so overall, there's like an optimal range of y speed here. So you can see the curve is increasing and then decreasing, while faster x speed generally makes catching harder. It monotonically decreases. And the effect of initial height is similar to that of the initial y speed, that there is an optimal range. And as the graph below, we fix the initial throw angle to be 45 degrees. And you can see for moderate heights, for like 0.5 to 2 meters, a higher throw is easier, but at much greater elevation differences, Fritz's mouth mechanics is the limiting factor, as in for like 5 meters, the radius is significantly slower. And predicting a parabolic trajectory is not a straightforward task, so it's understandable that Fritz struggles to learn. As he gains more experience, the error coefficient AX mentioned before will decrease, so Fritz will be able to catch bigger objects. And let's look more closely at the relatively subtle initial y speed effect by keeping the x speed constant. So these colored lines represent the different error constant. So at 0, that means Fritz has no error of the linear approximation. And if it's 1, like the linear approximation will take full effect. And so when the y speed is low, like in this region, the error mainly stems from the parabola misestimation, where Fritz can improve this through learning. So like at 0, it's pretty good. And then when the error is bigger, it significantly decreases. And when the y speed is high, however, mouth mechanics will be the limiting factor, which is harder to improve by learning. You can see all the curves just monotonically decreases. So if the owner wants to make Fritz look bad, he should throw at a higher y speed, almost straight up vertically.
Error resistance. We used the quadratic drag equation to incorporate error resistance and simulated the results for 3 different objects. We found error resistance makes catching easier, which may seem counterintuitive, but it makes sense because when drag is high, the vertical speed is close to the terminal speed, which better matches the dog's linear approximation. The speed will slow down in x, but it's way less than the effect of gravity.
So if the object is non-spherical, the dog has to predict the rotation of the food and twist its head to match its mouth to the nearest point. Additionally, long and rigid objects have to be caught in the center of mass, else they'll fall out. And deformable objects bounce less, so Fritz can catch the edge and hold on. So the center of mass rule is only true for rigid objects. So overall, the most important factors of the throw to Fritz's success are the throw speed, the horizontal component of velocity, and the size of the object. On the other hand, the most important factor of Fritz's behavior is his ability to predict the food's parabolic trajectory in the terminal phase when Fritz cannot see the food he's catching.
And here's a summary of our model. It centers on the idea of whether Fritz's mouth opening is wide enough to fit the object, which is this formula, and is divided into 3 parts: the mouth timing, position error, and angle of alignment, which is further affected by factors such as the initial throw, the mouth mechanics limitation, Fritz's experience, and other factors such as air resistance and the object's shape, size, and orientation. We use differential equations for the mouth opening and kinematics for the distance and angle calculations, and furthermore, an AI tracker to supplement getting the constants. And all of these combine to a complex relationship between the final mouth radius and the different initial parameters, and whether the size of the food will fit in with that radius.
So although this model is quite complex, it does not account for everything. In the model, the dog has good enough control over its body to move its head to the position it intends. It also correctly perceives the food position and velocity up to the point where it breaks eye contact with the mouth. Furthermore, only spherical objects were considered mathematically, so we didn't model rotation in flight. And finally, if the food bumps into the lips of the dog, we assumed the catch was a miss, which may not be the case for floppier foods.
So our work generally received positive feedback from the judges. However, there's still very great room for improvement. And one notable critique was that our video lacked clarity in fully specifying the problem. And given the complexity of our model, there were instances where the audience could not follow our train of thought. And our order of topics can also be better organized. But like the actual presentation was only 10 minutes, so it's kind of difficult to cover all the details. And furthermore, we can also improve on the clarity and contents of our graph and diagram, and perhaps using like softwares like MATLAB to wrap them.
So we had many ideas for how to model this situation, but we had to use a framework that was simple enough to be fully developed in reasonable times. So we had to narrow the scope of the model to fit into our video in some ways.
And one of our unused ideas was a model for the dog's inherent visual limitation of the error. And we found it out to be for the error to have a square relationship with the distance. And so while this approach is like more accurately represents the learning independent errors, we decided to omit this error to stay under the video time.
And another idea that didn't make the final cut was an alternate ODE for mouth movement. And this accounts for the fact that a jaw physically has a hard limit on how far it can open. So you can see in this ODE, as R approaches R max, the resisting force becomes infinite, or tends to infinity. And this is not something the damped harmonic oscillator accounted for. However, developing this ODE and solving it analytically was too time consuming for the scope of this project. So we proceeded with damped harmonic oscillator because it matched the real jaw movement well enough for our purposes. So in this case, we learned that a more complex model is not necessarily a better one.
We used an AI to grab data, and we trained it using Ultralytics' yellow V8, but the AI really struggled to gather the points for certain clips of the dog. But we could have just used tracker video analysis, and we would have had pretty good points that way instead of using an AI tracker.
So to improve the model in the future, we could account for errors that persist once the dog learns to predict parabolas, account for odd shapes quantitatively, and include a stochastic error to account for random variation between intention and result that's inherent in living things.
We also watched a few other outstanding submissions, and one notable approach used Newton's laws to simulate the dog's body dynamics to move to the correct position and make the catch. And another team simulated a range of initial throw parameters and calculated the optimal place to intercept the majority of the throws, giving Fritz advice for against those parameter variations.
We also looked at other teams that also used AI, and one of the teams used reinforcement learning, which we found was pretty cool because we didn't think of. And so this exemplifies the variety of possible approaches to this problem, which is the beauty of creative problem solving. Lastly, we express our gratitude to Professor Landy, our coach, for providing moral support throughout the contest and training us in the weeks leading up to it. This concludes our presentation, and we thank you for your attention.
Do you guys have questions? Hi, Anna. I may not have heard you. I was on.
Hey, yeah, no worries. I don't think anybody has any questions, but we can keep this room open for a bit and
Yeah,
see if
sure.
anyone does. Well, if no one has any questions, thank you guys for presenting. This was really fabulous, great work. If you'd like, we can close this room and move on to our next sessions after this. But thank you again.
Okay, sure. Thank you.